Hello everyone, and welcome to this fourth video in the Unit 1 series on functions and absolute value functions. And today we're going to get into more of absolute value functions, but more so how we can transform them. So how we can shift absolute value functions and do lots of different things with them. Before we get into more absolute value functions, let's do our warm-up for today. And we've got these 6 problems here for you. So take a minute to try those. Again, try to use some mental math. All right, so let's take a look at number 1 here. 3 to the negative second power. We have worked with positive integers. We've worked with 0. We've worked with, we saw negative 1 in our last video. But with a negative 2 as an exponent, let's kind of see what the process there is. So let's take a look again at the pattern here with 3 this time. So 3 cubed is 27. 3 squared is 9. 3 to the first is 3. 3 to the 0 is 1. And every time we're dividing by 3. So if we continue this, and I'll bring this up here now. If we continue this on, we're going to 3 to the negative 1. Again, we're going to divide by 3, so we get 1/3. Divide by 3 again, and we get 1/9. 1/9. So 3 to the negative second power is 1/9. One thing you might notice is 3 to the negative 2 is the reciprocal of 3 to the positive 2. Do you see that? So if we were to go on and look at 3 to the negative 3, what do you think that would be? Yeah, of course, it would be the reciprocal of 3 to the positive 3, so it would be 1/27. So again, when we have negative exponents, the key word there is reciprocal. It's not the reciprocal of the exponent itself, it's the reciprocal of the base that you're working with, raised to the positive of that power. Or you can just look at this and you can kind of go from there. Number 2, graph f of x equals -1 for all x values less than 0, +1 for all x values greater than or equal to 0. So in our last video we looked at piecewise functions, and this is one of those. So just a rough sketch here that I'm going to draw for us here. This one's fairly simple. So y equals -1. That's a horizontal line right below the x-axis. So for all x values less than 0, so basically everything to the left of the y-axis is going to have a function y equals -1. So it's going to be a horizontal line going down here with an open circle, because at 0 it's not included. So it goes all the way to 0, but it does not include 0. On the right side of the y-axis, so for all x values greater than or equal to 0, it's at 1. So we start with a filled in dot up here at 1, and then we have a horizontal line there, and I should add arrows to the ends of these here. So kind of an interesting looking graph, a piecewise function here that is kind of interesting to look at. Again, this is not a continuous graph because these are not connected. But that's just another example. Moving on to number 3 now. Square root of 360 and then times 2. So anything that we simplify here with the radical is going to multiply by the 2 that's already out there. So square root of 360, again we want to break this up into multiplication that involves a perfect square. So 2 times, let's see, if you think about perfect squares, if you know your perfect squares, one of them is 36. And this is just 36 times 10. So 36 times 10. And if you were to pull out, maybe if you wrote it like as a 9 or something, 9 times 40, well, then you simplify the 9, and then you have to go back and simplify the 40, just like we're doing the 360 right now. So there might be multiple layers at that point if you don't pull out the largest perfect square, in this case 36. So square root of 36 is 6, so we're going to have 2 times 6 times the square root of 10. 2 times 6, of course, is 12 on the square root of 10. Number 4, more percents this time. 7% of 51. Again, let's take the numbers involved, 7 and 51. We'll multiply those together first, and then we'll adjust the decimal. So 7 times 51, let's do 7 times 50 first. 7 times 5 is 35, so 7 times 50 is 350. And then 7 times 1 is 7, so 357. 357. Does that make sense? Is that reasonable? Of course not. 7% of 51, well, let's see, 7%, let's just do some estimation real quick. 7% of 50, well, that should be half of 7% of 100. So 7% of 100 is 7, so 7% of 50 should be 3.5. So 7% of 51 should be a little bit over 3.5, right? So if we adjust the decimal here, it should be not 357, not 35.7, but 3.57. All right, what is the percent? What percent is 1,021 of 4,084? This one can be done because, using mental math at least, because we can quickly look at this and see that this times 4 gives us this. So it's a quarter of that 4,084. So therefore it's 25% of that value. And then lastly, if you weren't able to get this one using mental math, that's okay. All right, I want to show you a little way to think about this one. When you're looking at division, you really can sometimes think of it as a multiplication question instead. So for example, let's look at a simpler case. So 6 divided by 2. You're thinking here 2 times what is 6, right? It's a multiplication question. So let's go and apply that here. So 1.234 times what gives us 1,234? Let's think about it. 1.234 times 10 is 12.34. Times 100 would be 123.4. Times 1,000 would be 1,234. So this times 1,000 produces that. So therefore, this is 1,000. So it's kind of a little way to work around that one. All right, so good job with that. Let's go ahead and move on to our topic for today. Again, is absolute value functions. So that's our goal, to describe transformations of absolute value functions and create their graphs. But also to kind of go backwards to write absolute value functions given a graph. So to kind of go both ways between a function and its graph and then backwards. So here we have the parent function of absolute value. And again, parent function is the simplest version of that function type. So the simplest version is just the square root of x by itself, nothing else. That's it. Okay? But of course we can shift this function horizontally, vertically. We can stretch it horizontally and vertically. So we can do a lot of things with this, but this is the one we start with, the most basic form of the absolute value function. And that's where we're going to start and kind of see what we can do from there. Our goal, again, is to go from the graph to the function and function to graph. In this case, we want to take something like this. So there's some additional numbers in here. And we want to visually think about and be able to work with the graph of that function. All right? So let's get into it and let's talk about specifically this part right here, this interior addition and subtraction that could be happening. And there's 2 ways that I want to approach it with you today. One of them is what I call the undo method. You want to undo what's been done in the parentheses. In this case, we can kind of think of absolute value as being a parentheses. So absolute value of x, with that most basic form, let's think about substituting 0 into that. If we put 0 into that, absolute value of 0 is still 0. So 0 produces 0. All right? Now, let's pose a different scenario. We've got absolute value of x minus 4. Let's think about this now. If 0 produced 0 up there, what value would still produce 0 down here? So think about what value could you put in for x so that the output would still be 0? Well, 4, if we put in 4 here, that's 4 minus 4 is 0. Absolute value of 0 is 0. Oh, okay. So we put in 4 here to output 0. So let's think about that for a second. We put in 4 more than what we originally did to get the same output. So absolute value of x minus 4 made it so we had to put in 4 more than what we originally did. So that's going to shift it not to the left, or it might seem like it shifts to the left because the minus 4 here, but actually shifts to the right because we have to put in 4 more than what we originally put in to kind of undo what's been done to x on the inside here. Let's look at another case. Again, let's go back to 0 produces 0. What would produce 0 here? What value of x could we put in that would output 0? Well, you're probably thinking negative 6, right? Because negative 6 plus 6 gives us 0. Absolute value of 0 is 0. So negative 6 is what produces 0 down here. So up here we have 0 produces 0. Here we put in negative 6. That's a shift to the left 6. So x plus 6 on the inside actually shifts the function left 6. So again, we're undoing the addition of 6 in here by shifting it to the left 6 and putting in 6 less than what we originally did up at the top here. So that's kind of the undo method. I've heard some people refer to this as maybe it's the opposite sometimes. Or the inside is lying, but more so it's undoing what's been done to x to get back to that parent function that we started with, and so it's the opposite of maybe what is here, but more so it's undoing that process. So a second way to think about it is what I like to call minimizing or maximizing, but we'll get to that here in a second. Sorry, I got ahead of myself. Let's look at another case. So same undoing process. So we have 5x squared minus 6x plus 1. I looked this up by putting in 4 for x, actually gives us 57. So an input of 4 outputs 57. So I want you to think about down here. Here we're looking at f of x plus 7, which means we're taking anywhere there's an x up here, we're putting in x plus 7. So by writing this notation, we're saying put x plus 7 in for any x in the top equation. So I want you to think about, well, what value could we put in for x here that would also produce 57? Well, you kind of know what should take place, right? Because if we put in 4 up here into these x's, shouldn't we also get 57 if we put in 4 for these whole sets of parentheses? So if this whole set of parentheses is 4, if that whole set of parentheses is 4, okay, so we still have 5 times 4 squared minus 6 times 4 plus 1. Well, what value of x makes those parentheses 4 again? Well, x plus 7, we want it to equal 4. So that should be negative 3, right? Negative 3 plus 7 would give us 4 again. So negative 3 gave us 57. So instead of putting in 4, we actually put in negative 3 now, which is 7 less than 4. So we're moving to the left 7 instead of to the right because we're undoing this addition of 7. Okay, so once again, we're putting in 7 less than what we originally did, which makes it shift to the left 7. So again, opposite of what we might think in the parentheses here. All right, so no, that's a complicated way of thinking. All right, so this is the undo process. Again, as I said a minute ago, let's go on to the next one, which is maximizing or minimizing. So with absolute value, later on with quadratics, you can think of this idea of transformations shifting left and right as a way of maximizing and minimizing the function. Let's take a look. So what value can I put into x in that top one here that would minimize the output? So you might try some different values. -4. -4, absolute value of that is 4. Okay, can I do any better than output of 4? Well, let's try 2. 2, absolute value of 2 is 2. Okay, I'm even smaller, so I'm minimizing. Can I do even better? How about -1? Absolute value of -1 is 1. Can I do even better? And you're probably saying, yes, you can by putting in 0. So yes, 0 input minimizes the output, which is also 0. All right, so let's continue on with that same idea. Now I've got a different function type here. Think about again, what value would minimize the output? Well, it's whenever this whole piece is 0. Well, what makes this 0? Okay, let's think about it. It'll be 3 minus 3 is 0. So an input of 3 would minimize the output, which would again be 0. All right, so that minimum, that V part where the minimum of the V is going to occur not at 0, but now it's going to occur at 3, comma 0. All right, last one here. Now we've got something happening on the inside and on the outside. So let's see how that kind of impacts things. All right, let's try to minimize the output here. As you're probably seeing, it's going to be the same thing, right? If we input 3 here, that's going to make this whole thing 0, outputting 0 from this part, and we're going to add 4 to that. There's no way to minimize it and make it even any lower than 4. So an input of 3 still minimizes the output, but now the output's no longer 0. The output is now 4. So what we're saying here is the minimum value, the bottom of the V, occurs now to the right 3 and up 4. So at the point 3, 4 is where that occurs. Again, by thinking through a way to minimize our function. All right. Now, if we were to tack on a negative in front of this, how does that change things? Now we're no longer trying to minimize the output, but we're trying to maximize the output. And you'll see why. If you try different values here, you're going to get varying quantities out, but 3 still maximizes the output. So let's see how that is. So 3 minus 3 is 0. Absolute value of 0 is 0. Negative 0 is still 0. It's still outputting the same value there. Any other value you put in for x is going to result in some sort of negative number coming from this to go with the 4. 0 is the only one that isn't impacted by this negative. So put in 3, you get out 0. Negative 0 is 0 plus 4. So negative, all it does is it changes this. So we're inputting 3 still, we're outputting 4 still, but instead of it being the bottom of the V, it's the top of an upside down V. That's all that changes there. So still thinking through, and going back to our undo process, you can think of undoing this. How much would you need to do to undo the minus of 3? Well, you'd have to add 3. So it'd be to the right 3, and up 4. This negative, all that does is flip it upside down. All right. Okay, so let's move on and let's look at the graph of this. Okay, so let's go back and talk about this one here. Y equals absolute value of x minus 3 plus 4. So again, it's a shift to the right 3 and up 4. So right 1, 2, 3, and up 4. And we still have that V shape here with a slope of positive 1 going in that direction and negative 1 going in that direction. Forever and ever on both sides. All right? So that's just an example of one and how we can graph it. So hopefully you've got an idea of how to shift left and right. That comes from the inside of the absolute value. And then how to shift up and down comes from the outside, the addition or subtraction on the outside. So if we had a -6, well then it would be right 3 and down 6, and then the V would open from there. All right, so we've talked about how H impacts things, and we've talked about how K impacts things. But let's talk about the other two, A and B, and we'll also throw in some more about H and K as well. So let's go back to some Desmos here. And let's take a look at this. So you can see the same setup up here that we had in the last picture. So let's see how each one impacts the graph here. So A is the number in front of the absolute value. So if we increase A, so if we start at 1, which is where it kind of is an assumed 1 if we don't write anything in front. If we increase that, see what happens. See how it stretches it vertically? It stretches it vertically. If we decrease A, you can see the compression happening here. So we're back at 1. If we decrease it to be like 0.6, something like that, it compresses it vertically. And then if we go negative, as we said a minute ago, there's a negative value out in front. It becomes concave down. We talked about concave a couple videos ago. Concave up, concave down. So now it becomes concave down. It's opening downward. And again, if we go a larger negative, it's going to stretch it vertically as well. All right, so that's how A impacts things. Let's make it 1 again. And now let's go to B. How does B impact things? It's going to be hard to kind of tell this one. If we increase B, it looks like it's stretching it vertically, but in fact it's compressing it horizontally. I know it's a weird concept, but it's compressing it horizontally. Why is that? Why is a larger value compressing it? You would think a larger value would stretch it, but a larger value compresses it because B is on the inside of the absolute value. And remember, on the inside, we're undoing things. So if we multiply by 5 here, it's actually going to compress it by 1/5, by a factor of 1/5 on the inside. Because to undo a multiplication of 5, we have to divide by 5. So that's actually a compression horizontally. If we go back and we go to something less than 1, it's going to stretch it horizontally. And then if we go negative, the same thing actually happens. And you can probably imagine why that is. Why does negative act the same way as a positive? Well, because it's on the inside of the absolute value. So that's why, because absolute value of 5 is the same as absolute value of -5. Okay, so let's make that one 1. So we've got a vertical stretch or compression, horizontal stretch or compression, and then H, we've already talked about H. H is the one on the inside that shifts. So if I increase H, I'm going to make it plus here instead of minus. If we increase H, it actually shifts it to the left, as we thought, right? It's the opposite of what we might think. So as we increase H, it shifts it to the left. As we decrease H, it shifts it to the right. And then the K value that's on the outside, again, that shifts it up and down, just as we might think. So if I increase K, it's going to shift it up. If I decrease K, it's going to shift it down. All right, so let me give you a quick example. Going back to that, if you remember the car video that we watched maybe 3 sessions ago or something, the car got closer and closer to the camera, and then it got further and further away as it passed the camera. But did the car actually touch the camera? Was the distance between the car and the camera ever 0? It wasn't, right? There was actually some space in between. Let's assume it was 2 feet. There was 2 feet in between the car and the camera when they were at this closest point. So the graph would look like something like this. The car starts far away and then gets really, really, really close. It gets really, 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 really close. Did it actually touch it? Was the distance, if this is distance over time, the distance between the camera and the car, did it actually ever touch the camera? No. It only got to about 2 feet away from the camera, and then it got further and further away. So that's where these transformations might help take place. And this shows that it was maybe almost 4 seconds that it got closest to the camera. So we can transform these graphs to model these real-world situations. All right. So I'll leave you with this. Let's do some practice here. So I want to give you this graph, and I want to give you a moment to see if you can graph it on your graph paper. So take a second to do that. Okay, so we think about the different things going on here. We've got a shift to the right, or sorry, to the left 2, and then down 1, 2, 3. And so that's going to be our vertex, if you will, of our absolute value. The negative indicates it's going to open downward. So it's going to open downward. And since there's no A value, it's just going to be an A value of 1. So the slope on the right and left are just going to be 1 and -1 over here. If there was some A value there, we'd have to adjust and compress vertically. But there's not. And so this is the main kind of thing that you need to be able to do, is the horizontal transformations. But I really want you to think through this process, because these concepts that we're talking about today, where we have A, B, H, and K right here, these 4 quantities impact graphs of all sorts the same exact way. So if you can really grasp this concept right now, that's going to pay off when you get to quadratics, when you get to exponential functions, all kinds of different things. Every function follows these rules. All right. So really continue to think through that. Do some practice. Maybe pull up a Desmos and play around with some different functions there. All right. So with that. We'll go to our goal for today, which was to be able to graph absolute value functions, look at transformations of absolute value functions, and then go backwards, given a graph, come up with a function, or vice versa. So with that, I'll conclude this video, and we hope to see you in Unit 2, which will be the beginning of quadratics.